All right, folks, what should be a pretty short video here today, nice and straightforward. Just a little bit of background information, hopefully not too overwhelming, before you continue on in Chapter 5. Section 5.2, just like Section 5.1, is mostly an exploration lesson. We'll get back into more of the longer lessons when we get into Section 5.3 as we get a little bit more comfortable with our rational functions. Now, here we see our introduction to rational functions. A rational function can be expressed as a division of polynomial functions, meaning we've already worked with some kinds of rational functions before where we have 1 over q of x, which is a reciprocal function, like we studied in section 5.1. Could be q of x, could be f of x, could be g of x, whichever you prefer. Now, a rational function, though, will also have a polynomial in the numerator. So you'll have a polynomial in the numerator divided by a polynomial in the denominator every time. That's what makes up a rational function. And I apologize for that barking there from Sadie. I hope that wasn't too bad on your ears, folks. I don't think I'm going to edit that out, but we'll see, because it takes a lot longer to process if I edit. Now, reciprocal functions, like I said, that we studied in section 5.1, they're a kind of rational function where our numerator just equals 1. Well, we're going to study more complicated rational functions today. So the quotient of two polynomial functions, again, that creates a rational function, which often has one or more asymptotes. We have worked with asymptotes before. We've worked with vertical asymptotes. We've worked with horizontal asymptotes. We're also going to learn about one more kind of asymptote in here today, but we're not really going to rely on it too much other than recognizing certain situations where it happens. Now, holes we have talked about as well are point discontinuities, and that means it's a specific location where a function does not exist. So it will occur in a function, in a rational function, at a point x equals a if your numerator, p of x, and your denominator, q of x, each have a common factor, x minus a. All right, so that means if we have a function like this, where f of x equals x plus 1 divided by x squared plus 3x plus 2, we can find out where it might have any holes first by factoring. We'll bring it over here. F at x equals x plus 1 divided by x squared plus 3x plus 2. So first by factoring the denominator here. So we're working with x plus 1, which is already factored, my numerator, and my denominator, x plus 2, x plus 1. Okay, so I can see that they share a common factor of x plus 1, right? That's a factor in my numerator and in my denominator here. And that means that I would have a hole at x equals -1, and that is the root of the common factor. So this one would have a hole at x equals -1. All right, now let me see here. And in fact, I could, if I get a little bit further in here, I can say, okay, well, I know my denominator is not allowed to equal here -2 or -1. And so my final function, if I were to, and I'm just looking ahead a little bit here, this could cancel out and it would look like a reciprocal function that we've seen, except it also has a hole. So x cannot equal -2, which we already know because there would be a vertical asymptote there, or -1, and that's where there is a hole. All right, so again, so a hole happens at the root of a common factor between your numerator, in this case p of x, and your denominator, q of x here. Now, looking a little bit further, a vertical asymptote. We've already looked a little bit at our vertical asymptotes from our studying in section 5.1. A vertical asymptote is what we call an infinite discontinuity, and that means it's a discontinuity where your function is approaching plus or minus infinity, and it will occur at in our rational function if our denominator, in this case we call it q of x, if our denominator equals 0 after we have simplified. And that means sometimes we'll simplify like we did in the previous example. Sometimes we'll simplify first, so this kind of problem would have a hole at x equals -1, but it would have a vertical asymptote at x equals -2 because that's a root of a factor of my denominator. I'll say that again, that's a root of my factor of my denominator where x equals -2. So there would be a vertical asymptote there after I have simplified. You cannot have both a whole and a vertical asymptote in one location, okay? You have one or you have the other. We always need to check for wholes first before we look for vertical asymptotes. Now, for example, that same function that we just simplified, like I said, it would have a vertical asymptote in blue here at x equals -2. All right, I know this might feel like a big info dump. You can return back to this video and use it as you work through the examples as we continue below. Now, next we'll take a look at horizontal asymptotes. And in this case, we can have a few different things going on. So if our rational function f at x equals p of x over q of x, so that's, again, a polynomial divided by another polynomial. It's a polynomial in both my numerator and my denominator. That means both my numerator and my denominator have degrees. Okay, so if the degree of my numerator is less than or equal to the degree of my denominator, then I will have a horizontal asymptote in my function. Okay, well, let's look a little bit deeper. If the degree of my numerator specifically is less than the degree of my denominator, it's not equal to, but it's less than, then I will have a horizontal asymptote at y equals 0 every single time. If we think about that one for a moment, the degree of my numerator being less than the degree of my denominator, I can compare that to the work we did in section 5.1 with reciprocal functions. Well, a reciprocal function is 1 over a polynomial. It doesn't have to be a polynomial. We've worked pretty much strictly with polynomials at this point, and that's a good thing. So a reciprocal function is 1 over a polynomial. The degree of my numerator here is 0. The degree of my denominator, if it's greater than 0, that's what we studied yesterday, then we would have a horizontal asymptote at y equals 0. Well, that's great. This is lining up with other things that we have already studied. Okay, now my rational function will have a horizontal asymptote at y equals, so it's at a different location, not y equals 0, but y equals a certain value. And this certain value can be calculated by taking the leading coefficient of my numerator and dividing it by the leading coefficient of my denominator if the degree of my numerator is equal to the degree of my denominator. So let's take a look at an example like so. If I have f at x, zoom in a little more for you here. If I have f at x equals 3x squared plus 2x minus 1 divided by x squared minus 3x plus 7, then I can take a look just at the leading coefficients of my denominators, of my numerator and denominator. So my leading coefficient here is 3. My leading coefficient here is hidden. It's 1, right? 1x squared. So here I would have a horizontal asymptote at y equals 3 divided by 1, that's y equals 3. And if you would like, you can put that into Desmos to double check it. Okay, we're looking to have a horizontal asymptote at the leading coefficient of my numerator, which is 3, divided by the leading coefficient of my denominator, which is 1. All right, and lastly, folks, one more in here. My rational function will have a, oops, we're working in orange, will have what we call an oblique asymptote or a slant asymptote if the degree of my numerator is greater than the degree of my denominator. Now, a slant asymptote we would sketch, you know what, you will see as we go along. A slant asymptote is where as, say, x approaches infinity, y might approach a, say, x plus 3 or something like that. It might approach a linear function, right? So your function could look something like this. We can really work with a little bit of complicated functions as we get into these reciprocal functions. You'll sort of see as you work with Desmos in the future how as you work with Desmos in this lesson, you'll see what a slant asymptote kind of looks like. Okay, now what I would like you to do is I would like you to try it out. We have an order of a procedure as we try to sketch a rational function here, and I would like you to try and use Desmos. Don't necessarily just throw it into Desmos at the start. Please don't do that. But first, analyze the function, make some predictions, draw a little bit, and then try to determine what your function will sort of look like. Okay, so the procedure that we want to follow if we're sketching our functions like this, number one, we want to check for holes. So just like I said up at the beginning here, sorry, I know I'm jumping all over the place. I know you're probably used to it by now. A hole is a point discontinuity that occurs in our function at x equals a if my numerator and denominator have a common factor. So the first thing we want to do with our function, if we're trying to sketch it, is we want to check to see if there are any holes. We check to see if there are any holes by factoring my numerator and denominator. Here I'm working with x minus 3. My numerator is already factored. Divided by x plus 3, x minus 3. Okay, so I can see right away I have a hole here. Oh, a hole at, and really I'm going to be a little bit less picky than this. I apologize for changing your notation, but we're just going to write the x value. So there's a hole at x equals 3. That's the root of the common factor, because x minus 3 is a common factor. We can use a little bit of shorthand here. Okay, now after I recognize that hole, then I can cancel that out. I can say, okay, x cannot equal positive 3. And I can cancel out this common factor, leaving me with 1 over x plus 3. Don't forget that 1 over. 1 over x plus 3. And then we can take a look at this, and we can say, okay, just like in section 5.1, this is now a reciprocal function, right? So we checked for holes. We did that by factoring. Next, we're going to check for vertical asymptotes, and those are going to come in where my denominator equals 0. Okay, so I can set my denominator equal to 0. That's x plus 3 equals 0, and that means that x equals negative 3. So there's a vertical asymptote at x equals negative 3 because x plus 3, let's try to keep this nice and neat, because x plus 3 is a factor of the denominator. And lastly, the horizontal asymptote. And this one might take a little bit more out of you. I apologize. This list isn't in your work on your note, but you can take a screenshot here or copy it down for your own leisure. This will be uploaded on the classroom like usual. Next, we want to check for horizontal asymptotes. Okay, so here we're comparing, again, the degree of the numerator versus the degree of the denominator. So let's take a look back at our problem here. Okay, the degree of my numerator, well, that's 0. The degree of my denominator, that's 1. And then we can go up to our rules right here. The degree of my numerator here is less than the degree of my denominator. That means I have a horizontal asymptote at y equals 0. Horizontal asymptote at y equals 0 because the degree of my numerator is less than the degree of my denominator. Okay, so for each of these functions, after you have analyzed it like this, then I would like you to sketch in any asymptotes that you found. So we found a horizontal asymptote at y equals 0. We found a vertical asymptote at x equals negative 3. We know there's a hole, but we're not going to sketch it in quite yet because we don't know the y coordinate of this hole, and that's okay. We could find it, but I'm not going to overly worry about that at this point. And lastly, after we've checked for holes, vertical asymptotes, horizontal asymptotes, we can check for roots. Okay, so a root we know is going to be where our numerator equals 0. In this case, we have no roots because my numerator is simply 1. There are no variables up there, so there are no roots, and you can try it out. Then I want you to go into Desmos, take a look at the general shape of the function, and do your best to sketch that in there. I would like you to finish the rest of the problems on here. There are 8 different equations to look at. You will find your first slant asymptote, and you will find a new rule with asymptotes as we go through.